All right, minimizing coins from the CSES problem set in the dynamic programming category of problems. This is the second problem in that category. I'm not going to read the instruction, you can read the instruction yourselves. But the case here is that since it's DP, we're going to be reusing results to previous subproblems, right? So let's draw the relations that the subproblems have with each other. So here we can just draw the subproblem for position I. So let's say that, so essentially what we need is to find the result for a certain X. So for a certain sum of money that we're trying to produce, we want to know the minimal amount of coins needed, right? So let's say we are searching for the solution for DPI. Which are the previous solutions? So for any X less than I, which are the values that interest us to create the answer for this one? And the answer is, we're looking at all the possible coins. So let's say we have a coin with value number 1, a coin with value number K, and a coin with a value number F. Let's say we have only these 3 coins, okay? And we're going to prove, we're going to show the concept with these 3 coins, and the same concept applies for all types of coins. And we know that we have at most 100 coins, okay? So for every such subproblem that we are trying to solve, we just need to check these 100 coins at most. And how many subproblems can we have at most if n is the maximum, so 100, and x is the maximum value that we need to, the maximum sum we need to construct. So we only need to look backwards, and we are going to look at each sum individually. Then it's 1 million. So 1 million times 100, that's 100 million. And if we have just 100 million operations of constant time, they will pass through this 1 second time limit for sure, right? So an x times n solution, O n times x solution. So O n times x, just put the star here. This complexity should suffice to pass the problem. And also, like, again, we have 1 million subproblems. So essentially, these are going to be just integers. So 1 million integers, that's 4 bytes per integer, 4 million bytes. So 4 million bytes are less than 512 megabytes for sure, right? So let's prove the concept here with subproblems. So let's look at the coin with value I, for example, okay? So the solutions we have for which subproblem are interesting if we are going to use this coin as the last coin we're going to use. So the answer is dpi minus 1, right? So for all the solutions for this amount, for this sum here, so for sum I minus 1, for all those solutions, for the best solution, not all those solutions, we're counting the best, we're counting the number of coins we need for the best solution, right? So for the best solution, so the best combination of coins that has the minimum number of coins being used to produce I minus 1, I need one more coin, so this coin with value 1, and then my sum will be equal to I. So I can reuse the solution to this subproblem, to the subproblem for I minus 1, right? By just using the coin with value 1. So for K, so let's look at the other coins. So let's look at value K, for example. So again, I can just use this coin, and then I will get the optimal solution I have for I minus K, okay, which I already know. Okay, that's what we assume in dynamic programming. We assume that we already know solutions to smaller subproblems. So the size of the subproblem is essentially defined by the sum that we are searching in our case. So I already know dpi minus k. So I know the minimum number of coins I need to construct I minus k. And now by using a coin with value k, I can have a sum I. And if it's not apparent to you, it's because I minus k plus k equals to I, right? And the same goes for a coin with value f again. So here I'm going to need dp I minus f, which is a smaller subproblem because we can only have integer positive values for our coins. So I minus f, this is for sure smaller than I, right? We cannot have a zero value coin either. So yeah, so that's the subproblem I need. So the best solution I have for this subproblem, I can reuse it. I'm going to add one more coin to that solution, and then I can check and see if it's a better solution for my case I here. So let's say that this subproblem needed 4 coins to be created. This could be created with 2 coins, and this could be created with 5 coins, okay? So what's the best solution you can have for I? You're going to look through all the coins. So let's say we have 4 plus 1. So now the best solution for I is 5, right? Then we look into the next one, and we can see that, oh, we have an even better solution. It's 2 plus 1 coin, that's 3 coins. Then we look into the other case here, which is 5 coins and 1 more coin, that's 6 coins. 6 is greater than 3, so we discard this solution and we pick the solution we had from this subproblem that we saved from this subproblem in this case. So that's the logic behind this problem. So let's look at the implementation here. So C will be the array of coins, so we have at most 100 coins. I'm using 101 positions here to index from 1 until n, all right? And then the same goes for the sums that we are looking for, the subproblems we have. We have x reaching up until 1 million, so we have at most 1 million. We have 1 million subproblems. And again, I have this one here for numbering from 1 to use 1-based indexing. Then I read n and x as they are given in that way. So first we have n, then we have x, and then we have the coins. So I just have a loop here, and I read, here I'm reading coin I minus 1 for some reason. Yeah, I just fall back into the 0-based indexing. It doesn't matter. And then the base case here, which is having a sum of 0. So if the sum we're looking for is 0, it's not a possible input, but just intuitively, if we are not going to have any coins, then the sum is 0. So that's the only way you can have a sum of 0, which is having no coins, right? But in our case, dp0 is, yeah, that's the solution. For dp0, so for a sum of 0, we need no coins, essentially, right? So that's the solution for dp0. Then we start from a sum being equal to 1 up until the sum being equal to x, which is the answer we want to output. Every time we reach a new subproblem, we put this value here. Why do we put 1 million and 1 as the solution for something that we haven't solved? That is because the minimum coin we can have a value of 1, and we have at most 1 million being x being at most 1 million. So 1 million 1 coins, that's 1 million coins used, plus 1 coin more, then that's so the maximum. We're not gonna have, there is no case we're gonna have 101 million coins being used. That's 1 million is the most we are going to use, right? And that's the proof. So now for every subproblem, we're going to try and utilize all the coins we have. So from the first coin up until n. Again, here I'm using 0-based indexing. I don't know why I wrote this way, but yeah, we're just gonna have this minus 1 for every coin we're looking at. And for the, okay, so J essentially, J minus 1 will point to the coin we're going to try and use, okay? So if we try and use coin J minus 1 here, we're just going to subtract from the sum that we have this coin, okay? And we are going to see that this gives us a non-negative value, because if it gives us a negative value, so if you have a sum of, if we're trying to construct a solution for a sum being equal to 5, for example, okay, that's the goal we're trying to reach a sum of 5, and we have a coin with value of 7. Obviously, you cannot use this coin to construct a solution for, let me just write this more clear for you. We're trying to find the P5, for example, and we know that we have a coin that has a value of 7. We cannot use this coin into any solution for this subproblem, since just using a single coin will be greater than the sum that we are trying to construct. So this is a check here. We're checking that it's not greater, so we can use that coin. And then the other condition that must be true is that there is indeed a solution for this subproblem that we are looking at. So I minus the coin that we are looking at has a solution in our DP table. If it doesn't have, it's going to be 1,000,001, which we know it's translates into there is no solution. So if there is a solution, how are we going to use this solution? We're going to update our position, which is choosing the minimum between the already calculated best case, which is this one if we haven't found any solution yet. So DPI, and then we utilize the solution we found for I minus the coin that we're going to use, plus 1, because we're going to use that coin. So it's one more coin that we're going to be using. And that's the solution. We get the minimal each time, and that will give us the best solution to our sum that we are looking at. And we calculate up until x. If at the end of the day, the best solution we found for x is 1,000,001, which means there is no solution, we just put -1, since the instruction wants us to print -1 if there is no solution, and then we just print the px. So that's pretty much the solution to this. Again, this is very similar to the first problem, the dice combinations problem, where you just utilized solutions from previous subproblems to solve for the current condition. This time we are not counting the ways we can create a sum, but rather we calculate the best way in which we can create the least amount of coins needed to create that amount of sum. So that's pretty much for Minimizing Coins. If you like the video, leave it a like, subscribe to the channel, and I will see you in the next one.